Hello, welcome to this online lecture that will be kindly given by our guest lecturer, Professor Luigi Vanfretti from RPI USA. Yeah, it is a very interesting topic. Following our discussions a couple of weeks ago in the workshop on the dynamic stability of electrical power systems. And today he's going to tell us details about some of his latest work on the area. Welcome, Luigi. Well, the screen is yours now.
Okay, thank you very much for hosting this. And so the topic that I decided to present has been work that has gone for a long time with different collaborations. The idea is that how do you design experiments to be able to do identification in the system? And to do that, to prototype things, we use power system models based on Modelica. So it combines two of the areas that I mostly work on into one. Okay, so I'll do some acknowledgements and I'll spend some time on the background. And then I'll tell you about the SysID techniques that we're using and the problem formulation to design these optimal input signals. And the last part is a little bit about prototyping on how we build these models. And of course, we will discuss, Jose has organized another event where I'll do the hands-on training workshop on how to use these Modelica tools. I don't remember the date, but I have it somewhere later in the presentation. So this work, as I mentioned, is it's been going for a while at different stages and different components. So this is basically more or less a presentation that is putting together a lot of papers. The collaboration and the funding is from Supergrid Institute in Lyon, France. The École Centrale de Lyon, where I did my visiting professor position last year. And this year, I'm not a visiting professor, I'm just a visiting researcher. But I'm, again, here continuing that collaboration. And Dominion Energy has supported my students. The first person that started working on this topic was Dr. Vedran Peric, who's in TU Munich. And he started working with Professor Xavier Bombois, who is in the CNRS in France, here in the ECL in Lyon. And then we had a postdoc together with that continued this work at Supergrid, who's Short Boersma. He's Dutch, and now he's in Wageningen University. And yes, my students have also contributed, and I want to also acknowledge Abdel Krim and Chetan that had been the project managers to support the work. So as you see, there's a lot of people that has been involved for a while. Okay, let me start with the background. So typically, you know, when we do power system analysis, we have computer simulation models, and we can do many types of analysis with them. If the models are validated for a given bandwidth, and usually if they're validated for a large bandwidth, they are able to capture nonlinearities. In the case of PMT models, you have a large bandwidth. In the case of RMS models or positive sequence models that I mostly focus on, they have a lower bandwidth. But the issue is that it's very difficult to maintain these models with the required accuracy and precision and use, especially if you want to do near or real-time grid dynamic monitoring and control purposes. So it's pretty hard to have a well-validated model that you can use continuously over periods of less than 5 minutes or within an hour. It's very challenging to do that. So the idea is that we can alternatively use other types of models. And, one type of model is a simplified transfer function representation. And this as an example, there's different kind of representations, but think about a transfer function, which is something that we all know from electrical engineering basics. Now, the nice thing about these simple models is that they can be identified from real-world measurement data, both during normal operating conditions, what we like to call sometimes ambient data, or during large disturbances, so you lose a line and there's a big transient. But more importantly, you could also do stage tests, or basically what I like to call experiments. And in this case, you can actually inject a signal into the system, into control inputs, to conduct these experiments for identification. And by doing this, you can target improvements in accuracy in terms of what you're identifying in these simplified representations. Well, yeah, these models will be limited in bandwidth, right? Because they're limited by the measurements themselves. They have a Nyquist limit, the type of measurements that you use. So if you think about PMU measurements, you already have a bandwidth limitation of 25 or 15 hertz due to Nyquist. But they can give a very useful representation of a group of characteristics. So for example, you can characterize the critical grid dynamics over the frequency range that you desire, or that, an entire one if you want to do that. And that is very useful for two things. One is for monitoring, and the second one is for control design. I will not talk about control design because it's kind of the work that we're doing last year and right now. We'll talk mostly about monitoring, but you can use it for redesign of controllers. So that's useful representation has these two applications that it would be really hard to do that on a continuous basis with conventional grid models. So identified models are useful. And the other thing is that we can actually specify constraints on the required accuracy and precision of estimated parameters. So for example, if I estimate a transfer function and I get the denominator, I can extract the poles. And from there, I can get the frequency and damping of each of the grid dynamics. And what I can do on top of that when you do an experiment is that we can specify constraints on the accuracy. So we can not only get damping and frequency, but also we can get the variance. And the variance is a very important quantification that we need to do that helps us to tell the quality of our estimate. So just to illustrate, what are we, what are we trying to characterize, where these measurements can help? It can help answer the dynamics that the system of the system that are being excited. So here at the beginning of this recording, you could actually use this ambient data to characterize the damping deterioration that obviously you see here is going up. So this growing envelope is a result of damping degradation, and you can tell over time, if you take snapshots of data by rolling windows, you can tell if the system is becoming stable or unstable, and how much, right? So that's the quantification that we're doing that. So to identify the model that captures this kind of behavior, we will assume that the system operates in a quasi-steady state condition. So you see these little wiggles going around right here on top of the data. It looks like noise, but inside of noise, there is information about the system dynamics. We also will assume that the system is only excited by these small changes, so we don't have to wait until there is a big loss of a line to identify the dynamics. We can do it continuously on a rolling basis. And then if we assume those two things, we can approximate the system to a linear model in discrete time. So instead of S, we have Z, and G hat is the estimated transfer function of the system from an input to an output. And so in A of C of theta, where theta is the parameters that we need to estimate, we will find inside of theta what we estimate as the parameters, the critical information of the system dynamics, which, for example, is all of the modes with estimated damping and an estimated frequency. Okay, so here's a little bit of background on the system response. So if you have an input to G, the real system is G, and the identified system is G hat. You could have random variations on the load. So here I'm simulating just random noise on a load. And the output would be a random, well, it would be the response of G to these random load changes, and it will look something like this. We could also have a probing signal. So we design the signal to have a certain characteristic, and we will have the system response to that system characteristic. And finally, we could have a transient, and we will have the response to that transient. So in total, you have a whole response of the system that has different components, right? You have this transient one, then you have the ambient, and then you have the probing. And from these three types of data, you can estimate the system dynamics. So we will focus in this talk. There's a lot of methods for transient. The most popular one is probing. There's a lot of methods for ambient. The most popular one is the Yule-Walker method. But we will focus on the ones due to probing, because we want to be able to design experiments that improve the accuracy. So we, under the transient and the ambient response, we're not having any influence on the system. We're not designing the signal. So we cannot really put constraints on how accurate we want that to be. Okay, that's the concept. So let me give you a little bit of a background about the transient response first. So in this slide, what you can see is that it's a real world grid experiment, and this these experiments continue to be conducted. Actually, you can find them. They do this in the western part of the US. So that's why I have the original picture here. This is the response of the system during this event in 1996 with the system break apart. And that was the motivation to be able to do this dynamic monitoring. So when they started doing this dynamic monitoring, they creating this thing called the Chief Joseph Dynamic Breaker. Is one of the few facilities in the world that allow you to inject a shunt resistor, basically. This is what it is. And, well, you can actually control, or, well, not control, but you can actually apply a transient into the system. So here you have an experiment at the top, and you see the resulting grid dynamics for inserting this device. And then at the bottom, you can see what they obtained as the measurement output and the estimated model that is able to characterize a 0.3 hertz mode in the Western interconnection of the US. So this, the interesting thing is that this is a very, very intrusive test. You know, it is it can consume 1.5 gigawatts almost, and it will burn if it's on for more than 3 seconds. So this is a very aggressive experiment. So you kind of don't want to do those kind of ones, but I would love to have one of this. Okay. So what about the ambient response? So the same event in 1996, people started thinking, well, you know, there were a lot of events that happened. So for example, here you had a line trip that went before when they run, if you run the estimation, you get a 7% damping. And then the damping degraded with the change of system operation, and the damping was 3.6. Now here you have a lot of time that is passing that you can use just this data in real time or near real time. No, it's not real time, it's near real time to obtain damping estimates. So that was the concept that, okay, we have, can we just use the blue sky data to estimate, or the ambient data to estimate what is the damping condition? So you can see here in the slide, this is the screen that they had in, so they created the concept of this mode meter. So as you see, the system undergoes its normal operation, you can track what is the damping, and then you can put some bounds on the damping. So if it's more than 5%, you should be okay in theory. And then as it degrades, maybe you trigger an alarm so that maybe you can do something about it. Like the easiest things to do is redispatch. And then if the damping degrades, you can go into emergency operations. But the idea is that you have almost more than 2 minutes here to do something before the system, if it has another event, it does not go unstable due to that event. Okay, so that's the concept of the mode meter. And you see here in the bottom of the screen, you have two modes that are being tracked, 0.25 and 0.38 hertz. This is a spectrum that shows you the peaks. So for depending on the frequency is here on this axis and time is under this axis. So it tells you the peak of the activity of the mode. And here at the bottom, you have the estimation of the damping ratio on this axis and the frequency. So you can see how these little guys are moving over time. Okay, so that's what you would do under blind conditions, under ambient data. So then the question is, like, are these estimates any good? Because you know, the system conditions are changing, but you don't have any really influence on the data that you're getting, how the system dynamics are being excited. So the question is, are these estimates any good? So here's an example. If the true frequency, if the true damping is 0.1% and you get an estimate 0.09, is it any good? You don't know unless you look at the variance. So the variance depends on the mean. So if your mean is higher than the true value, that means that you have bias. But more important than bias is variance. And basically, if you do these estimations 100 times, you create this histogram and you look at the result from the estimation. If you have a lower variance, that means that your estimate is much better than a large variance. So tracking the mode is not the only thing that you have to do. You also have to track the variance in the estimated parameters of damping and frequency. And finally, in order to achieve lower variance, what you can do is do the probing signals. So here is the real world case that I know where they actually conduct this routinely. These are all pictures, but they're good pictures. So, and this is a test from 2005. I couldn't find the picture for the 2005 test, but of the estimated model. But here you can see the estimated model of the, so the peaks show you the 0.20 something and the 0.30 something. These are the two peaks that you're trying to track. The different lines are different estimation methods. So here you see they're doing this experiment where they inject that breaker twice. So they have some data too, because they don't have the ground truth from this. They only have the real world. They only have measurements to do this, okay? So when they introduce these breakers is to establish what it should be the damping more or less that you're getting, so that you have some idea. And then you can see here that they introduce a probing signal, and they do that through the control signals of the HVDC link. Right here, this DC Pacific intertie line is called. And they introduce a very low amplitude signal. And this low amplitude signal will allow us to enhance the response that you get during this period to do identification. Okay, so that's the procedure. Okay, so the state of the art on these experiments in the real world is what they do in the western of the US. And basically, they create a signal of plus minus 20 megawatt. And with that, they excite the system through HVDC link. You can find a report of the recent experiments that they did in 2021. I think they're doing them this year too. Now, how do they design this signal? Here, the signal is designed with a priori knowledge. So they've been doing this for a while. They have a knowledge on how much is the bounce. So I actually found out that the plus minus 20 megawatt, it was a specification from BPA that they didn't want to put more than that into of this random signal into HVDC link. Now, the other things that they know is they want to limit the maximum energy in the peak to peak. So they adjust the phase of the sinusoids that they're injecting. They limit the frequency from 0.1 hertz to 1 hertz. So you see right here, this is the amplitudes of the sinusoids that they're injecting. And when they arrive to 1 hertz, they have this decay on the amplitude of the sinusoids that are injecting. And they apply it for between 10 to 20 minutes. So these experiments, because you're introducing a small signal, they have to be long so that you have a lot of data to do the identification. You can improve on the accuracy by having long experiment, okay? If you have a very short experiment, then your accuracy suffers. So the longer, the better in general, but of course you cannot do, it doesn't make sense because how the system operating conditions change to do it more than, let's say, 15 minutes in some cases. Okay, so here is the research that we've done. First, how to design signals for systems where you don't know so much about the dynamics. So these guys have been studying that network for more than 30 years. They know the dynamics very well. You can look at this report where they analyze the transition even of these dynamics over time, over the years. But what happens when you don't know that much? That's a challenge because how would you design the signal? And second of all, is if you have change in dynamics. So if you install things, if you lose plants, and this is something that we have been experiencing in Europe. I say we because I'm in Europe now, but so over time, the system changes, and how do you adapt that signal? The next question that we wanted to answer is like, can we reduce the effort of the controller by minimizing the impulse signal's spectral power, the power inside of the spectrum, not the megawatts, okay? So that's one question. And the second one is, can we limit the impact that we give to the system? So can we make this the response of the system to be almost unnoticeable by minimizing the output signal's spectral power, so the power under the spectrum, all while maintaining high accuracy and precision in estimated parameters. So our mode estimates should be of high quality. And finally, the last research question is, how can we test the design signals before we attempt a field trial? So how can we do this closer to reality with hardware-in-the-loop simulation? So that's what we wanted to show. All right, so how do you do these things? You need some magic from Professor Xavier Bomboes, who I'm going to meet in after the talk. And this is tools from the field of system identification, and the invention from Professor Bomboes that is called least costly experiment design. Okay, so the basis, let me cover, as good as I can, because I'm not a specialist on this. I just work with my friend and he teaches me. So let's assume, right, that the real system is defined by two transfer functions. One is called G of Z and one is H of Z. We're doing it on discrete time, and then we will transform what we do in discrete time to continuous time with Tostin approximation, for example. Okay, so Y over here is going to be the measurements that you obtain. E is the disturbance, but this disturbance is actually just the load randomly changing in the system. And that is going to excite this H of Z. So H of Z is the yes. So the H of Z is the transfer function between E of T, these random variations, and the response of the system to random variations. And then we have this U of T, which is our input signal that it's either deterministic. So just like they're doing in that report, that, okay, this is the shape of the signal that we want. So you put it in, or you design it in the approach that we will discuss. And that will give you a transfer function between U of T and Y of T. And the sum of these transfer functions, because remember, we're assuming that we're under these ambient operating conditions, is what you get in the measurements. So in system identification, really the goal for this problem is going, or in general, actually, this is the general framework, is to obtain estimated. So the hat is for estimated, G hat and H of hat of the model. So these are discrete times transfer functions for a given U, where theta is the unknown parameter. Okay, so theta is going to be the parameter vector, which are the coefficients of our transfer functions that are going to be estimated. And once we estimate these coefficients of the transfer functions, we can extract, by converting from discrete time to continuous time, we can extract the damping and the frequency of the modes. Okay, so with system identification, we get an estimated model of G and H, and we can use that to monitor. And the second thing is experiment design. So the design with the constraints on the accuracy and the precision will allow us to do better monitoring of these two functions. And of course, once you have G, which is between the input, is the transfer function between the input and the output, so you can actually redesign the controller that you have. I will not cover this in this talk. Maybe I can do another one once they accept our paper. Right. So that's the concept. The key technique used here is going to be the prediction error method. So in the prediction error method, you have the true system response modeled by S. So S will have G0 and H0. So that's the real system. And you have the input E and U. And what we're going to do is to build the build a prediction model that is G and H hat. So you have the true system on top gives you the output Y, and the estimated system at the bottom gives you Y hat. So what you can do is that you can take Y, subtract Y hat, and calculate the error. Now, if you apply that error signal to the inverse of H, if you have good estimation of G and H hat, then your E should be the same as the noise of the system. Okay, so that's the methodology is very elegant. You can see how pretty it is, easy to understand too. That basically, if we have a good estimate of these two transfer functions H and G, they are more or less as close as possible to the true system. Then this E epsilon of T has to be just white noise. So we assume in this work that the random source variations are independent, and we do not make any assumptions on their probability distribution function. So they have a shape and a variance, and we don't assume anything about them. It's just going to be random data for us. So in sum, the prediction error method is stated as find the estimate of the unknown parameter vector theta, that is the coefficients of the numerator and denominator, which will give you a good G hat that minimizes this epsilon. Of course, you can never get this to be equal, but you will minimize it using a set of n input data. So this is finite amount of data of this form. So you have U and Y obtained from the true system response. Okay, so that's the summary. Great. So I talked about a lot about this transfer function. So you have to choose a model structure, and because we have an input, we use an Armax model. You can use any model you want. You can use a Buck-Jenkins structure, whatever, right? But the key here is that you need a model structure that relates you from the input and the output. And when we talk about model structures here, is basically how our transfer functions look like. So our estimated G is going to have a B of Z over an A of Z. And here you have this delay multiplied. And our H of C is going to have a Z of Z and an A of Z. And all of them are a function of the estimated parameter vector. The estimated parameter vector has three subvectors that are theta A, that is the denominator. That's where we have the poles of the system. Theta B is the zeros of the numerator of G, the system response. The true system response, and to U, and theta C, that is the numerator of the response to the noise, the estimated response. Hat is all the estimated transfer functions. So we have all of this turning to be these coefficients. Okay, so it's A times, if you remember continuous time, so it's going to be A times S squared plus B times S plus C, for example. But here we have it in the form of Z. So we have B0 plus B1 times Z, and so on with all the orders of the model. So this is our model structure. Now the problem is that if you estimate theta, you have coefficients of the polynomial. You don't have mode frequency and mode damping. So the research result that we have, and I'm not going to go through the details because it's like 5 pages of math that Short did. What we did is a reparametrization of the model where we changed theta A, where the poles and, that we're looking for, we represented as theta zeta, which now is rewritten in form of the dampings and the frequencies to the mode. So in this way, instead of having to do estimating the theta parameter and then do a transformation to continuous time and extract the damping and frequency, we do it directly with the reparametrization. Okay, so the original model that we have here, M, I forgot to mention the optimization problem. Where the estimation of theta is to solve this optimization problem where you're trying to minimize E, which is the error between Y of t and Y of t hat. So by minimizing this, it should approach to be like white noise. You're minimizing the power of the signal. Okay, so making it white noise means that you're minimizing it. Okay, so as I was saying, our result was that just obtain, when you're doing the estimation of the thetas by reparametrizing, the result is now that we don't have to do the transformation, we get the damping and the frequencies directly. Okay, so this is a very good result. It's all analytical, what Short did. And the challenge here is that you need analytical and symbolic expressions that are derived in the paper published 2 years ago now. It's just getting stale, but it's still my favorite stuff. I'm still working on these things. Okay, so with that, what we do now that we have a model structure, we design the probing signal. So we will use a multisine time domain realization. So basically a sum of cosines with frequency omega r, phase omega r, and magnitude omega alpha r. Now, the power spectrum of the signal is basically psi u of omega is basically a Dirac function. So that means that the input signal, if we use the multisine realization, that is only going to depend on the magnitude. Okay, the power of the signal is only depending on the magnitude. Okay, so in optimal design, which is described in detail in this paper from Professor von Boys, what we do is define the objective of the identification problem. So in our case, U of t should minimize the control effort and at the same time minimize the disturbance in the network while ensuring a user-defined upper bound for the damping estimation variance. So this is our goal in the design. The framework allows us to do this in this way. So here we're going to solve this optimization problem. We're going to minimize the spectrum of the input signal by doing what? We're going to have two components. We want to attack the controller effort and we want to minimize the impact on the system. So psi u is going to be the probing spectrum of the signal. Theta u is the output signal spectrum. Nabla I over here is our constraint that we want to minimize the variance to a user-defined value. Let's say we want the variance to be less than 0.01. And C1 and C2 are weights that allows us to prioritize either minimizing control effort or minimizing impact to the system. So that minimizing the first term of this equation results in minimal effort from the controller, and minimizing the second one results in a probing signal which provides a spectrum that doesn't excite frequencies that you don't want to excite too much, basically. So the trade-off is here is in tuning C1 and C2 by trial and error, is basically, or by doing different simulations in our case. Okay, so using this framework, what we're going to do now is that we're going to rewrite the problem in terms of our G hat, or estimated model, and H hat. If you do this, remember that the input signal is a Dirac delta, so the power of that signal is only determined by the amplitude AR. Okay, so that's great. And then we put add a second constraint that says that this should be larger than 0. So you avoid any negatives because it makes no sense to have a negative amplitude in a signal, okay? And the second term, you see here, we have the power spectrum square of G. So here, basically, we're calculating the spectrum of G and multiplied by the amplitude of R. And we're multiplying these two. So this part is to minimize the control effort, and this is to minimize the impact of the system. So following the procedure that we have in the paper, I'm skipping the details, but the end result is that we will obtain the optimal signal. And the optimal signal is simply going to be determined by the coefficients of the cosines and the sines. So these coefficients, we'll find them by this optimization problem. And omega r is going to be an array, a grid of values for the frequencies that we're going to inject. So from 0.1 to 1 hertz was the example from those guys. We can do it any range that you want. And theta r is chosen randomly. And the reason that we're choosing this randomly is that we allow, when the cosine starts, we can move it around. And that guarantees that the input signal amplitude is at the level that we desire, basically. Now, there is a tricky thing that to solve this problem, you need to compute something called the covariance matrix. And this is not easy. So there is all the results in Short's paper. If you're interested in the math, it's interesting, actually, but don't want to bore you with details. So what is the result of this potential if you create these input signals? Take a generic multisine that you have not designed and you just put it in. Well, a generic multisine will just inject frequencies at the range that you wanted. So here we have the frequencies, and you inject all over the place. What we do is that we're just going to inject where it matters, basically, either or to minimize the controller effort or the impact of the system. So you see here now that we're only probing a certain amount or a given frequencies, and the other ones are set to 0 by the optimization problem. Okay. All right. So how do we apply this methodology? So we will do two things. We'll have a base procedure, so a first experiment that gives you a base knowledge of what is the base. So you don't have any information. You're just working with measurements. So you need to estimate G to start from, okay? Before you do you can obtain an optimal signal to improve the accuracy, okay? So you simply use U-based a multisine signal, a dumb multisine signal. And you obtain this theta base, and you obtain the covariance matrix, okay? So that's the first experiment. And then we're going to do the optimal procedure. In the optimal procedure, we have two steps. We have the injection of U1, and based on the injection of U1, we inject the optimal signal. So the first experiment is basically just injecting a multisine again. And the second part of the experiment is to inject the optimal U. In the first experiment, we will calculate the user-defined variance, okay? So what this means is that we're going to calculate the variance of the multisine that you have here, and we're going to say that the constraint on the variance is that you have to be lower than what you get with a multisine. So that's the idea of the first experiment. So if you inject a multisine, you'll get a variance. Well, if you're going to now make an optimal signal, the variance that you get on the damping estimate should be lower than with a dumb signal. That's basically the concept. And so this approach allows us to ensure that the optimal input signal spectrum has lower spectral power too. And basically, we apply the optimization process to create this optimal input signal. Okay, so now we have here some results. So the first example here, we have assigned 0 to the minimization of the impact of the system. And here we're going to say just prioritize reducing the control effort. Okay. What we're going to do in this experiment is this is a single machine to infinite output system. So here you have the generator with these controllers and so on. And here you have the output signal that we're going to use for estimation. The output signal, as you see here, is taking the angle difference between the bus 1 and bus 2. And we're going to, the input signal is going to vary the reactive power injected by a StatCom into here, okay? Because we have a model, we are not in the field doing these experiments, right? We have a model, we actually can linearize this model and tell you the ground truth of what are the modes and the damping. I know the ground truth because I can linearize this model. I know exactly what it is. So this is the powerful thing of using these Modelica models. So the true value is 1.1, and for the damping, and sorry, for the 1.1 for the frequency, and the damping is 8.2%. Sorry, 7.9%, and we are obtaining 1 hertz of the estimate of the frequency and 8.2. Now, this example is made for illustration, because if you see, our signal is only 2 minutes, so you're not going to get good estimation. But what I want to show here is, if you look here, we have the U1 and the U optimal that we're applying. And at the bottom, we have the fitness of the model, basically. So we can get a good fitness of our model when we compare to the real data. But what is important here is that the optimal signal batch is 20% higher than U1 batch. Why does this happen? Well, because we have decided not to minimize the impact on the system, but to minimize the control error. Okay, so that's a result of our choice here. But what is most important is that now you can see that U1 is the multisine signal, so it's at all the frequency grid that we define. It has an amplitude, but now our optimal signal, as you can see here, only has a few frequencies. So the resulting optimal signal you see has a lower amplitude to minimize the control effort, and it's only defined at the frequencies that we need to excite the system to obtain a good damping estimate. Now here's a second example where we choose to minimize the impact on the system. So it's the same system. We do the cross-validation, so we have good models. They have a good fit. We have the estimated is 1 Hertz, and now we got a closer to the damping estimate. Why did we get closer to the damping estimate? It's because we chose to minimize the impact into the system, while at the same time trying to address the impact on the controller. But what's more interesting here is that by doing this optimal signal, you see here how the shapes looks different from the multisine. This optimal signal has actually 40% lower power than the multisine. Okay, so in the power spectrum, this is 40% lower. And if you look at the result here is that now you're targeting only a few frequencies, but the amplitude is different, you see? Right? The amplitude is different at a few of the frequencies. Oh, sorry, I went too far. You see the change? So we have improved it, basically. That's the idea. Oh, yes, I forgot to mention that the random low variations are, where are they here? E1 and E2 are connected to, yeah, so these are, I don't remember where they are, sorry. Okay, now for the HVDC, that was all the motivation. Here we have the Kundur-Klein-Rogers 2-area model. I call it like this because it was all of them that did it, not just one guy. And it has a VSC HVDC link connecting these two. If you're not familiar with this model, let me just summarize. It has one inter-area mode on this area, one inter-area mode, inter-area, no, it's a local mode that is only making these two areas interact. Another local mode that make these areas interact. This is 1.1 Hertz, and this is 1.3 Hertz. We are not targeting the estimation of those modes in this example. We only want to reproduce what they're doing in the Western US, that is an inter-area mode, and that's between this area and this area over here. And it has that mode has a frequency of 0.63 Hertz in this model, and a damping of 0.015. Okay, the input signal is going to be a change in the reference on the power through HVDC link, similar, trying to reproduce what they do in the field. And the measurements is the angle difference between bus 7 and bus 9 on the AC side. Because you see this system over here, the HVDC link, is in parallel with the AC side. And here is with the AC mode travels, basically, right? We don't have a damping controller here. That would be the next stage to apply a damping controller to improve the inter-area mode, but we're not doing that. We're just doing monitoring right now. So that angle difference gives you very good content on the signal to do the identification. And if you want to discuss that, I wrote my PhD thesis on how to find that. So it's been a long time now. So here are some results. If we minimize the controller effort by and don't care about the impact on the system, you have this optimal signal being created over here, and the black line is where the inter-area mode is. Okay, so the first thing that you notice is that we are not excited on all of these frequencies, so we get only of these few ones. And if you notice, they are around the frequencies of the modes that we're trying to estimate anyway. So you're just shaking them enough to improve the accuracy on the estimation. And as a result, you see here, the DOM input signal is relatively larger than the optimal signal. And in this other case, we are prioritizing the impact of the system without concerning too much about the controller effort. And what you get here is that a substantial reduction on the amplitude of the signal. So this is the key. If to convince the operators of doing these experiments is to tell them, we will do inject as small as possible signal after we've done the first experiment. So from this point on, you just use optimal signals, because until the system changes, then you need to repeat the procedure. But if you look, this is a substantially, sorry, no, it's not substantially lower. It's, I kind of messed up the point here. 0.7, I was going in the other direction. Anyway, we're guaranteeing that we're injecting a low signal, but that we get a good variance, but it's still very tiny anyway. You can see here in terms of the amplitude, right, of the total signal. So even this was the point that we're trying to make. Even though these coefficients here, so the amplitude of these few frequencies are higher here, the total signal that you're injecting is lower than the multisine, okay? The multisine is already pretty small anyway. Okay, so quality of these estimation problems. Because we're using Modelica models that you can perform symbolic linearization with, you actually know, you can calculate from input to output the transfer function. So you just take the ABCD matrices, you put them in Python or in MATLAB, and you get the transfer function between input and output, the true one, and that's in blue. And you can see in the blue one, you have these local modes that you cannot see with the signal that we chosen so well. Because in this, when you use these two signals over here, there's going to be mostly in the signal the content of the inter-area mode. So that's by design. And effectively, the true transfer function shows us that. Now we have G base, the one that is for reference, and then you have G of 1 that is for case 1, and G of 2 for case 2. And you can see that we have very, very good fit for the inter-area mode. And this range is not a great fit, but that's because our signal has very low information in it. Well, that's one point. The other point is because the model structure, it will not be possible to estimate these modes very well with the model structure that we've chosen. Why? If you look at the total system mode that, model that we have, it has 46 states. Sorry, has 46 poles, whereas the RMAX structure that we chose has 4 poles only. Okay, so with 4 poles, you cannot estimate the 6 modes. That's why we don't capture those there. But what we do capture, we capture extremely well. And why do I say extremely well? We do these estimations 100 times, and then we calculate the mean and variance of each of the signals. So we find what? That the mean is going to be 0.18, 0.16, and 0.17 in these cases. Or variance is going to be lower than the base procedure you see here. In this case it's higher. Why? Because we didn't choose to minimize the impact of the system, and here we chose to minimize the impact of the system. And then the normalized probing power is reduced in the 2 optimal experiments. So it's lower in these 2 optimal experiments is lower than the multi-side. And the impact of the system in the measurement is also lower. So we are able to achieve both with this approach. Most people in the review papers like to always complain that you didn't use a big system. I don't see the point because we're doing research, we're not deploying this in the field. But you know, if you are one of those that wants to see the same result with a larger system. In the paper, there is this Nordic 44 that is a massive network. Okay, so that's all for the optimal experiment design. Now, you heard me mentioning these Modelica models to generate the data and play as if it was the real measurements. Well, I cannot do experiments because I don't have a real system to do experiments on, and I'm not in the club of the BPA and the people that works with them that do the real world experiments. So I cannot do them, but in the absence of these models, we can use first principles, physics-based models. They're indispensable because they can provide you the ground truth to develop these methods. Now, the problem with this power system simulation models is that they're locked into a specific tool like PSSC, Dix Island, whatever, and they're not portable. So if you do it in PSSC, very hard that you get the same answer in Dix Island. So that's a problem. Second of all, and pretty important when you're trying to do this kind of work, is that these tools do not have symbolic linearization. Okay, so you can't really get a linear model from the equations of the nonlinear system. Basically, you have to re-implement from scratch somewhere else, like MATLAB BSD or PSAT, which is the common tools to use. Now, the problem with MATLAB BSD is that it uses numerical perturbation, which is not as good as symbolic linearization. And PSAT, well, you have to put the symbolic expression, the partial derivatives yourself and program them if you are using a new model. So even if you have some symbolic linearization facilities, it's not that easy. Well, even if you have this ability to do these cases, this case with PSAT, you can run this simulator to do hardware in the loop testing, to test the input signal as you design it, inject it into hardware and create measurements. So you can test the injection device and what happens in that stage, or if you want to put the controller. So if you want to bring this closer into practice, it's very, very hard. But we can do this with Modelica and the functional mockup interface standard. Now, Modelica is an equation-based object-oriented language. It's not a software. It's not a tool. There are 9 tools that support the language, which you can find in the Modelica Association website, and the functional mockup interface standard, which allows to export Modelica models so that you can use them in 150 different tools, and you can find more about the standard there. It's very successful standard. It's adopted by industry outside of power. Even in power, you have EMTP-RV that now uses it. I think Dix Island Power Factory uses the functional interface standard for importing. So it's being adopted in power, but forget about power tools doing full adoption of it. Look at the website and you'll see a full coverage of who's doing what. So this is a very successful standard. So that means one model, single model across all of my purposes. And that's why I've spent more than 10 years with PhD students, friends, developing the OpenIPSL, the power system modeling library based on Modelica language. So our main goal is to basically be able to have all the capabilities of time domain simulation, linearization, everything provided by the Modelica tools. And our job is not to build a simulator, but just to make the models and guarantee that they give you the same answer than PSSC for what we have implemented. So here you have a picture where we have two Modelica tools comparing to PSSC. The library now supports you can use 5 different tools at different levels, and we will discuss that in the mini tutorial. If you want to see results of the verification of our models against PSSC, you can go to this link. Again, this is actually the time where I will give a demo. But since Jose has asked me to give the mini tutorial, I'll give a Delft again so we can record it. I'm not going to do the demo today so that we get more people coming to the mini tutorial, and I'll show you how it runs in different tools, and you'll get to build your own model. Anyway, I showed you some pictures of these Modelica models in our examples before. So how do you use them for real time? Well, what we do is that we have our offline model. We add the outputs and the inputs into it. So the outputs is where the measurements we're going to have, and the inputs is our probing signal that we're going to inject. Then, using a Modelica tool called Dymola, we create an FMU, and an FMU is the exported model according to the FMI standard specification. Okay, so the FMI standard describes how the model should be exported. We export the model with a feature that includes the source code. So the model that we're exporting here, we have a license that allows us to do that with Dymola, will include the C source code of the original Modelica model. So the Modelica model is, when it's exported, it is going to be compiled into, well, it's not compiled, it's transpiled into C in such form that it can be recompiled anywhere else. And where is once we have that, we use the DSpace Calexio. The reason that we're using this real-time simulator is that they are the only ones that have full support for the FMI standard that I have tested myself. So in DSpace has a tool that allows you to import the FMU and connect the input signals and connect a block for the output signals. And then this tool takes what you built and deploys it to be executed in real time here. So basically it takes all of that C source code and compiles it into a binary that can be run into this hardware right here. Okay, so here is an example of a real-time simulation. Here is the measurements that we get in the oscilloscope. They're also with a digital PC-based oscilloscope shown there. This is the simulation, and this is the signal, just a plain vanilla one. You can see some results in the previous paper. Explains the whole process of how to do this. And here is the probing experiment. So you see here, there's the input signal that we designed. And this is the output signal here, and this is our simulator. So, surprise, this is the same results that I was showing you for the single machine infinite bust example. I don't have to repeat the example because I already showed you the signals from it. This is what we did in real time. If you want to look at the differences between doing the real-time result, so included the signal injection and the data acquisition, you can read this paper here. So we have one model that we're reusing from offline to real time. The only thing that we do is that we add inputs and outputs, and then we compile it with source code as an FMU. Then this approach allows you to test the optimal signal before you use in real time. So you could even have a piece of hardware that generates the signal instead of how we did it here. So you can actually address the issues of real-world realization of the signal and of the data acquisition before you start doing the field trials. So there's a lot of things that happen just realizing the data, injecting it, and then acquiring measurements that you have to address. And this is an approach to address it. And we left at the proof of concept. Hopefully I can get some funding somewhere to address the hardware related aspects of doing this in the future. So here is my conclusions. The message is that we can design private signals to provide an optimal signal that has a power spectrum that minimizes disturbances in the network, while at the same time ensure that or upper bound on the damping estimation variance is low so that we have good accuracy. This is achieved with Armax model structure. You can use another one, but this Armax model structure has been reparameterized so that you automatically obtain the dampings and the frequencies, avoiding additional steps. And we are also able to solve this optimization problem that calculates the signal only by finding the amplitudes for a grid of frequencies with omega r chosen randomly. So that's the probing. This has a unique advantage that the effort of the controller actuator that drives you into the system can be targeted. We can also target the impact on the system, so we don't inject frequencies where it's not needed. So for example, we don't excite everywhere close to the low damp modes, only around them. So you saw that we have a line, and they were not exactly at the frequency of excitation, you see? They were next to it. So we don't necessarily excite the mode, we excite around it. That's the nice thing about this. And the method, we could also optimize the phase. That's something that we might do, but it's not really necessary when you use random phases. These improvements can hopefully steer the power industry to use probing more regularly, so that we can do better monitoring, but hopefully also improve the controller. So this especially, I think, is significant for all the issues that we're having with distributed energy resources, PV and wind, that are injecting frequencies at 22 hertz. Why are they injecting frequencies at 22 hertz, 11 hertz, whatever they are doing? It's because the controllers are not calibrated. So we could actually use this, detect the units that are injected frequencies where they shouldn't, and then with a good model, redesign the controller. And that's the work that I'm doing right now with Professor Bomboy. Since last year, we've been working on that. And finally, these two interpretable open access modeling standards, the Modelica language and the FMI standard, together with the Open IPC library, allows us to have one model from offline design to real-time prototyping. Is facilitated. We just need to have a good model, one, and we don't have to spend all the time re-implementing RSCAD or OPAL-RT stuff. It's one model, and we just have to add inputs and outputs. And I think this, as I said, this approach can be very useful for dealing with larger dynamics and oscillatory modes. In HVDC, you have ones that are going thousands of hertz, so we could try to target how to monitor them and control them with this approach too. And here are all of the papers that I summarized in my presentation. These are on optimal probing design. And this is the paper that we just submitted to SEGAN on the controller redesign. Hopefully I can present that after we get the paper accepted. We might have some, it would take long with these people. Anyway, and the three other ones are about the Modelica and FMI. And with that, I leave you with the ending slide of my university, and I'm open to questions. And thank you very much for coming. Okay, Jose. Am I? Oh, I took way longer than I should. You didn't say anything. Hello, Jose.
Yeah, it seems there are no questions, and even our second participant, Dari, is offline.
Yeah, unfortunately. Well, at least we recorded it so we can share it with everybody else.
So I think we can close the meeting, the webinar.
Okay, Jose, thank you for inviting me.
Thank you once again a lot, Luigi, for your valuable support.
Thank you so much.
My pleasure. And you know, whoever is watching this later, make sure you sign up for the tutorial. Hopefully, we'll have more people then.
Yeah.
Hey, send me the recording too, please.
Sure, I will stop now the recording, and I will share the links probably end of today.
Okay, Jose. Take care. Bye bye.
Thank you.
Thank you.
Take care. Bye.
Bye, guys. Thank you.